Today we will start chapter 8, which is column with uh, both axial load and bending. In chapter 5 we did column, but that time we had only axial load, no bending. This time we will have bending. Now if you read your book first few pages, you will learn how moment may come inside a column. And let me revise your book. At the beginning they define what is braced frame, what is unbraced frame. We know what is braced frame. There will be like diagonal bracing to resist the lateral load. In unbraced frame there is no lateral bracing, but all the joints are rigid. That is called unbraced frame or moment frame. Okay, so if I go even more, you can read everything. I am just skipping this to save some time. And how moment may come inside beam, inside column. One example is here. If there is a girder connected here or beam connected here, and that will apply some load, then there will be some moment this way. Also I drew a figure here. Do not see this first or this one first, then you will be misguided. First see this one. So here what will happen for this column, if the load in this girder or in this girder, in this girder, in this, so if this load and this load equal, there will be no bending this way. If there is load here and they are equal, there will be no moment this way. But what about here in this column? If the load here and here is equal, good, there will be no moment this way. But there's load here, there's no load here, so it's obvious that there will be some moment this way. uh, Now if there is, if this load and this load is not equal, then there will be moment about this axis also. So this column, at least there will be moment in one direction, may not be here, but there is a good chance. What about corner column? Yes, there's obvious that there will be moment about this column and this girder, and there will be moment about this girder. So this column, these four columns will get moment about both axes. The ace column, this one, they will get moment about one axis. Now something else, when we design a beam, we intentionally produce moment inside inside column also. How? So so this column will not get any moment if load here and here are equal. Now what do we do here? Sometimes we consider this floor is empty, this floor is loaded, then there will be some moment here. So that way we intentionally create some worst case scenario. Even sometimes in this side we assume loaded, this side is unloaded. That means there will be moment here also. So this way we produce some moment to consider the unloaded case, because if a building is so big, there is a good chance that one floor or one room will be loaded, other room will be unloaded. It is possible. So this way there are different cases moment may come, but the final statement is most of the column in this world has moment, whatever it is, reinforced concrete column or steel column. So today our topic is how to design a steel column for moment. Now, so if I go to your book, now to start designing, you need the previous knowledge that we learned from previous chapters. Okay, I'm scrolling your book. Let us see. Yes, this is something column schedule. It is important to understand. What is this? uh, Now again here just to understand. So the column takes the load summation from all floors. So load in this column is small, here loads will be larger, load will be larger, load will be larger. In this column load will be the largest. So we try to make different sections. So this column is bigger, this is little smaller, this is the lightest section in this column. So when there is a question of connection, we try to connect not in the junction, we connect in between the floors, roughly the middle or 3-4 feet uh, on the floor. Why? Because you saw in your structure analysis class is that moment is typically zero at the middle, not exactly middle, somewhere around the middle. So we try to connect column in between floors, not in the joint. Never do it on the joint because moment is the maximum on the joint. So this is the splice location where we will do the splice. So this will be one section, other section, other section, other section. We try to decrease the material. Now next table, this table is better to understand here. The bottom column is W840, 840, after sometimes 824, 824. That means this column is same size but it is heavier. Heavier means thickness is larger. Here same size column but dead load 24, or the self weight is lower. Why lower? Because the thickness is so small. So here when we design column, we show column this way, and their splice will be here, that is 4 feet from the floor. Now better to make it at the middle, but sometimes we do not do it. We do sometimes very close to the floor so that we can easily connect. So but do not do it in the junction, beam column joint, never, because over there moment is maximum. Okay, so yes, this page or these equations are the most important for this chapter. If you understand this page, you are very expert in designing column. So two equation to design column with moment. One equation is this, other equation is this. Now both equation uses similar parameter, just different coefficient. For example, if pu over phi pn is greater or equal to 20% or 0.2, this equation is our design equation. If it is not, then this is our equation. Here pu over phi pn, pu over phi pn, there is a 2 here, 8 over 9 here, there is no 8 over 9 here. So that is the change is 1 over 2 and 8 over 9. That is the only change between these two equations. So you need to understand all the parameters. Now the good news is that most of the parameters are known to you. Okay, if I zoom in, so what is pu? Pu is the applied factored load, axial load. Whatever the load we are applying on the column uniaxially, that is the factored load. What is phi pn? Phi pn is the axial load capacity of the column without considering the moment. So this is the load that we learned from chapter 5, the axial load capacity of a column. How to find it? Very easy. Just find the KL or KL by R. Go to the table, AISC table, chapter 4 somewhere. Find the section, find the capacity. So this is that. So very simple, this one. It is the load capacity using no moment. Sorry, using only axial load, no moment. So pu pn, now it is known. mux, there is a story here, here this portion, phi b mnx. What is this? It is the moment capacity of the column about x-axis. Moment capacity of the column about x-axis. Now this portion, you know it. How? Chapter 6, beam design. When you design excuse me, when you design beam, you actually found this one, the moment capacity of a beam. Now here we are doing moment capacity of a column, same thing. When you talk about moment, it is actually a beam. So this is whatever you learn from chapter 6, beam design. You have to find moment capacity of the column considering the unbraced length. So this portion you already learned it. This one you did not learn, but there is a very straightforward equation for this. It is at the bottom of this page. That is the moment capacity about y-axis. Moment capacity about y-axis. What is this? It is phi zy fy. Now zy can be found AISC manual chapter 1, or 1.5 phi b sy fy. Sy means section modulus, APY means yield stress. Now 1.5, this value changed in the recent revision, it is 1.6. Now this kind of coefficient you should not memorize, it always changes with time. Whenever a new revision comes, this value changes. So in the new revision, even in the recent edition of this book, it is 1.6. So you learn how to find capacity of the column about y-axis, and this one capacity of the column about x-axis after chapter 6. Now, so there are more discussion on ppn. I told you that it is the moment capacity without considering moment. Here are some guidelines here. So if it is a compression, now yes, if it is a compression member, you know that we need kl. So k, how to find k? Typically for breast it is 0.1, for moment frame it is 2.1. So here it says k is 1, is commonly used in practice. I told you to you earlier also. Typically we use k is 1. If you know more accurately, use the more accurate value, your result will be more accurate. So all the stories are done. Only I did not discuss AMUX and AMUI. That is something new, and that is something to discuss, and that is important, and that is the main challenge for this chapter. Okay, how to find it? Your book, oh, it is not here somewhere. Or maybe I skipped it last pages. Okay, maybe not here. Okay, I can find it. Okay, so if I go here, now I copied those two equation here so that I can explain better. So again, PU is the applied factor load, PP and axial load capacity without moment. How to find it? Just simply find KL and go to AISC manual table 4-sum table 4-x. In chapter 4 you will find the capacity of this section. This is the applied load. Now we discussed this one. What is this? It is the beam capacity. It is the beam capacity about x-axis. What is this? It is the beam capacity or moment capacity about y-axis. So MUX, how to find MUX? So MUX, it will be B1 MU, no translation, x. So we are doing here x, so everything here is x, plus B2 MU lateral translation x. Now what does it means? Yes, we will go there. Then what about MUY? So MUY, same thing, B1Y, then moment U, no translation y, plus B2 MULT lateral translation y. So it looks so difficult, but again it is very simple. What is MUX? Is what what is this part? MU means factor moment. What is NT? NT means no translation. That means this portion, the first portion is for breast frame, this portion is for moment frame. That means no bracing. No bracing. So if your moment is a breast frame, that means B2 is 0. is 0. So this portion is 0 if it is a breast frame. So if it is not, no, I'm right. If it is a breast frame, that means it is no NT, no translation. That means this is our case. So now what is this part, this portion? This is whatever moment about x-axis. After analysis, whatever moment you find about x-axis. I just wrote into, or your book wrote in NT, or the AISC specification wrote NT. The reason is to elaborate it. What does it mean? Means no translation, no translation. No translation means no lateral sway. That means for breast frame it is possible. What about x? About x-axis. What is bx? Bx means moment amplification factor. We need to increase the moment. Now, why do we need to increase the moment? I'm going there. And before going there, okay, what is this? MUY about moment about y-axis. It is whatever moment you found about y-axis for no translation in about y-axis. We need to amplify this. We need to increase it. Now we cannot decrease it. Whatever moment we found after structural analysis, we cannot decrease. We need to increase. So now we need to find what is B and why do we need B. Now before going there, I will erase everything. So make sure that you understood all parts of this. All parts is. So it everything you know it, you saw it only these two moment, which is moment about x-axis, moment about y-axis. Now how to find it? Whatever your moment, you have to amplify by multiplying b for breast frame. If your frame is moment frame, then you have to use this portion. In that case, this will be 0. But most of the frame are breast frame, so most of the cases this portion is 0. Now if it is a moment frame, a special case, no problem, you can calculate B2. So I will talk about B2 later. So today or this time I will talk about B1x. How to find B1x? Okay, let's go. Let us go to your book. So oh, my next question is why do we need to amplify? Yeah, this is case will tell you a lot. This is case or this portion of your book will tell you a lot. So if I have a column here, I have applied load here, some lateral load here. If I cut somewhere, the free body diagram is this. So if I take summation of moment here, what is my moment? W by 2 times L by 2. So my moment should be W by 2, L by 2. But due to buckling, there will be additional moment. What is that? The load here. If you cannot see here, so due to the buckling, this P times this delta, this buckling, that will produce additional buckling. So you can see in this equation, moment is WL by 4 plus P delta. Now WL by 4 is our actual analytical or theoretical moment. This P delta is additional moment. It comes due to the buckling. Now we do not know exactly what is the buckling. We do not know what is exactly the buckling. So what we do? We discard this, multiply a factor that is called B1. So we were talking a lot about what is B1. B1 is that portion. B1 will consider any moment which is coming due to the buckling. So that is B1. Now how to find it? We are going there. So you can see here they wrote here M is B1 MU NT. NT means no translation, BU means factor moment. So we do not know this portion, so we are multiplying B1. Now maybe next page, let us see where is B1. Now it is for B2 if your moment is sway possible or moment frame. But now we are talking about only breast frame. Yes, this portion of your book will talk about B1. So how to find B1? B1 is CM over 1 minus PU over PE1 now, and it must be greater than 1. Why? We can amplify the moment, we cannot decrease it. Now what is the value of CM? there is an equation to find it, or we can assume 0.85 to be safe. Now what is PU? PU is the applied factor load, you know that. Excuse me. What is PE1? It is the Euler buckling load. Euler buckling load, and you already saw it, how to calculate it. Pi square E over KL by R square. That is the Euler buckling load for that column. Now when we are talking about x-axis, it will be x, 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 x. When we are talking about y-axis, b1y, cmy, pey, and pu is the same for both ry. So we should consider the axis here also. Now how to find cm? Cm is this equation 0.6 minus 0.4 m1 minus m2. Now what is, okay, that means if there is a column here, and if the moment is this, m1 the larger one, m2 is this, so cm can be found 0.6 minus 4 m1 by m2. Now there is a negative sign here, because this moment, if it is positive, this is negative, so there is a negative sign here, so it comes 0. So yes, if the moment in both cases is equal, then it is 1. But to be safe, no need to worry about points cm. Always use point cm x or y, whatever it is, 0.85. It is somewhere in your book, so always use 0.85 to be safe. If you use this, you will be safe. So I will advise you not to worry about cm. Always use 0.5. Okay, now again, okay, if I go to your book, so hopefully I discuss all the theory required to design a column beyond. Now we did not talk about b2. Okay, let us see b2 very quickly. Yes, b2 is this equation. b2 is 1 over 1 minus alpha. Alpha is a factor. Pu, summation of pu, that means the total load on that story. If that story has 10 columns, then consider all the loads, and this is the Euler buckling load. Euler buckling load is the Euler buckling load for all the column of that story. If that story has 10, 20, 30 column, some of them. What is alpha? And alpha is a factor. It is somewhere, yes, alpha is 1 for LRFD. If we use LRFD method, alpha is 1. Now we always, or now we are using LRFD, so alpha is 1. So there's another equation to find b2. This equation I'm not going there because this is difficult. Not difficult, actually same. Any one equation is good. I'm just trying to save some time. Or I can tell clearly very quickly here. b2 is 1 over delta OH by L. What is delta? Is the drift limit. That means typically ranges 1 over 500 by 1 over 400. What is this? This delta OS is the horizontal deflection or the top of the building. So whatever the horizontal sway possible over L, the length, story to story or floor height. So this portion is typically assumed. It is not that you will calculate the drift or you will calculate the sway. You will assume something in between these two, and then summation of applied load on the floor. It might have 10 columns, no problem. Summation of all divided by summation of horizontal load in factored horizontal or lateral shear. Now this portion has lot of calculation. I like to use the other equation, the first equation for b2. This equation, it is easy to me. No, not this equation, the other one. This equation, it is easy to me because it is simple calculation. Summation of load on the all columns. This is typically known by this time. When we will design column, we should calculate load on the column. Very easy. And then Euler buckling stress or Euler buckling force for all the column. It's not so difficult. If you use Excel, it gives you in few seconds or few minutes. So this is easy to me. This is the way to find b2. Now when the b1 exists, b2 doesn't exist. When b2 exists, b1 doesn't uh, exist. So anyone. Okay, so we will see some example. Before the example we will take a break here. Thank you.